Suppose I hold up a jar, a glass jar, sealed tight, and I pump out all the air, every last molecule. Then I cool it down, way down, colder than outer space, colder than anything you have ever experienced or could experience. I remove every atom, every photon, every speck of dust, and every whisper of heat. What is left? Nothing. That is the obvious answer. That is what your eyes would tell you if you could look inside. And for about 300 years, that answer satisfied everyone. Empty space was empty, end of story. Except it is not the end of the story. Not even close. Because when I started calculating what nothing actually is, really calculating using the rules we know are correct, the rules we have tested to 12 decimal places of precision, something came out of those equations that should not be there. Something enormous, something so wildly, absurdly large that it made the entire universe impossible. And the terrifying part is not that the calculation was wrong. The terrifying part is that we still cannot figure out where the mistake is. Let me take you through it, piece by piece, like a detective following a trail of clues, because that is what this is, a mystery, and the suspect is nothing itself. Start with something you already know, even if you do not realize you know it. You cannot pin a thing down perfectly. That is not philosophy. That is not hand-waving. That is a law as firm as gravity. Werner Heisenberg figured this out in 1927. He showed that there is a fundamental limit to how precisely you can know two related properties of anything at the same time. You want to know exactly where a particle is, fine, but then you cannot know exactly how fast it is moving. You want to nail down its momentum with perfect precision? Good luck, its position becomes a blur. And this is not some trivial smearing out. This is not about measurement being hard. I want you to really feel this, because it is the key to everything that follows. Imagine you have a friend and you ask them, where are you right now? They say, I am standing on the corner of 5th Avenue and 42nd Street. Great. Very precise. But now you ask, and how fast are you walking? And they say, I have absolutely no idea. I might be standing still. I might be running. I genuinely do not know. That sounds crazy for a person on a street corner. But for an electron, that is exactly how nature works. The more confidently you can say where it is, the less you can say about how it is moving, and vice versa. The universe keeps a ledger, and the product of those two uncertainties can never drop below a certain minimum value set by Planck's constant. That is the tax you pay for existing at the quantum scale. All right, so what does that have to do with nothing? Well, think about what nothing means if you take it literally. No energy, no motion, no vibration, complete total stillness, zero everything. But Heisenberg just told us that complete stillness is illegal. If something has exactly zero energy and exactly zero motion, then you know both its position and its momentum with perfect certainty. Both are zero, and that violates the rule. Nature will not allow it. This is not a technicality, this is fundamental. The universe is physically incapable of producing a state of perfect rest. It would be like asking a river to flow at exactly zero speed and simultaneously be at a perfectly defined location. Quantum mechanics says no, something must be moving. Some residual tremor must exist. So what does nature do instead? It fidgets. Even in the emptiest, coldest, most desolate patch of space you can imagine, there is a tiny, irreducible jitter, a trembling that can never be turned off, no matter how hard you try, no matter how clever your technology, no matter how patient you are. Physicists call this the zero-point energy. It is the energy of nothing, the lowest possible energy a system can ever have, and it is not zero. Let me give you a picture. Imagine a ball sitting at the bottom of a bowl. In classical physics, the old-fashioned pre-quantum physics, that ball can sit perfectly still at the very bottom. Zero energy, done, dead still. But in quantum mechanics, the ball cannot sit still. It wobbles, it oscillates, not because anything pushed it, not because there is any heat left. It wobbles because sitting perfectly still is not an option in this universe. There is a minimum jiggle built into the system, and you cannot get below it. You cool it, you isolate it, you remove every possible disturbance, and it still jiggles. That minimum energy is 1/2 times the product of Planck's constant and the natural frequency of the oscillator. 1/2 h bar omega. Remember that formula. It will haunt us later. Now that is one ball in one ball. One little oscillator. Barely worth worrying about. The energy involved is inconceivably small. For a single quantum oscillator vibrating at the frequency of visible light, the zero-point energy is around 10 to the minus 19th joules. That is nothing. Less than the energy it takes to nudge a single molecule of air. Who cares? Well, it depends on how many bowls there are. And this is where the floor drops out. Because the universe is not one bowl, not two bowls, not a million bowls. The universe is full of fields. Not just one field, but many. And each field fills all of space. Continuously. Everywhere. Without gaps. Without interruption. Now, what do I mean by a field? I mean something very specific. That a field is a quantity that has a value at every point in space and time. Temperature is a field. At every location in this room there is a temperature. The air pressure is a field. At every point in the atmosphere there is a pressure. But these are classical fields made of molecules. The fields I am talking about are fundamental. They exist even in a perfect vacuum. They are not made of anything smaller. The electromagnetic field, for one, it fills all of space. Every point in that field, at every possible frequency, at every possible direction of vibration, behaves like its own little oscillator. Its own little ball, with a quantum ball jiggling at the bottom. And every single one of those oscillators has this minimum jiggle, this irreducible zero-point energy. How many of these oscillators are there? Think about it. The electromagnetic field exists at every point in space. And at each point there is not one oscillator but infinitely many, one for each possible frequency of vibration. Low frequency, high frequency, and everything in between. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, and beyond, up to whatever the highest frequency in nature turns out to be. You see the problem, there is no obvious ceiling. At every point and at every possible frequency you have another oscillator contributing its little bit of zero-point energy, its 1/2 h bar omega. And since omega, the frequency, can go as high as you like, and there are infinitely many points in space, you start adding them up and the sum does not converge to a nice number. It does not converge at all. It goes to infinity. Infinity. In every cubic centimeter of empty space. Now hold on. That sounds absurd. An infinite amount of energy sitting in every tiny volume of vacuum? That cannot be right. And you are correct to be suspicious. Physicists were suspicious too. In fact, for decades the standard response was, ignore it. Subtract it off. It is just a constant background. It is the same everywhere. It does not do anything. Physics only cares about energy differences, not absolute values. So set the vacuum energy to zero by convention and move on with your life. And here is the remarkable thing. For almost everything we do in quantum electrodynamics, that strategy works brilliantly. You subtract off the infinite vacuum energy, set it to zero by decree, and compute everything else relative to that baseline. The answers you get for real measurable things, like how an electron scatters a photon, like the precise magnetic strength of an electron, like the shift of spectral lines in hydrogen, those answers match experiments to breathtaking precision. Let me give you a sense of how precise. The magnetic moment of the electron, this is a number that tells you how strongly an electron responds to a magnetic field. We calculated this number using quantum electrodynamics, summing up contributions from Feynman diagrams involving virtual photons and virtual electron-positron pairs buzzing around in the vacuum. The calculation required evaluating hundreds of diagrams, some involving 4 or 5 levels of these virtual corrections. And when we were done, we had a number, and experimentalists went into their labs with their exquisite equipment and measured the same number, and the two agreed to better than 1 part in a trillion. 1 part in a trillion, that is like predicting the distance from the Earth to the Moon and getting it right to within the thickness of a single sheet of paper. So the theory works magnificently, spectacularly. No theory in the history of science has ever matched experiment this closely. And yet, there is this infinity lurking in the basement. This infinite energy of nothing that we chose to ignore. We shoved it aside because it was inconvenient, because we did not know what to do with it, because subtracting it seemed harmless. But is it harmless? Let me introduce you to a Dutch physicist named Hendrik Casimir. In 1948, Casimir was working at the Philips Research Laboratories in Eindhoven, studying the behavior of colloidal solutions. Not exactly the bleeding edge of quantum physics, but But he started thinking about the forces between neutral particles, and that led him to a conversation with Niels Bohr, and Bohr said something that changed everything. Bohr suggested the forces might have something to do with zero-point energy. Casimir followed the thread. He asked a very simple question. What if you take two metal plates, perfectly flat, perfectly conducting, uncharged, and hold them very close together in a vacuum? Classically, nothing should happen. There is no charge. There is no current. There is no reason for a force. The plates should just sit there, inert, bored, doing absolutely nothing. But Casimir realized something subtle. Those zero-point fluctuations of the electromagnetic field, the jiggling of nothing that I just told you about, they exist between the plates and outside the plates. Outside the plates, every possible wavelength of fluctuation can exist. Every frequency, every mode. The field can vibrate however it likes. But between the plates, only certain wavelengths fit. Think of it like a guitar string. A guitar string fixed at both ends can only vibrate at frequencies where whole numbers of half wavelengths fit between the pegs. You get the fundamental, the first harmonic, the second harmonic, and so on. You do not get every possible wavelength. The boundary conditions restrict what is allowed. The metal plates do the same thing to the electromagnetic field. Between the plates, only those vacuum fluctuations whose wavelengths fit neatly between the two surfaces, whole numbers of half wavelengths, can survive. All the other modes are suppressed, so there are fewer fluctuations between the plates than outside them, fewer modes, less vacuum energy density in the gap than in the surrounding space, and that difference in energy means there is a force, a genuine physical force pushing the plates together. Think of it like the pressure difference that holds a suction cup to a window. Except this pressure comes not from air but from the quantum vacuum itself. There is more nothing pushing on the outside of the plates than on the inside. So the plates get squeezed together. Casimir calculated this force. The formula is beautifully simple. It depends on Planck's constant, the speed of light, the area of the plates, and the inverse of the fourth power of the distance between them. Nothing else, no material properties, no charges, no coupling constants of any kind. Just the geometry of empty space and the fundamental constants of quantum mechanics and relativity. For decades, this was a theoretical prediction, a curiosity, a parlor trick of quantum field theory. The force is extraordinarily small. For two plates, a square centimeter in area, separated by about 1 micrometer, 1/1,000,000th of a meter, the force is roughly 1/10,000,000,000th of a Newton. That is about the weight of a single red blood cell on the surface of the Earth. Tiny, absurdly tiny, but tiny does not mean zero. The first person to try measuring it was Marcus Sparnay, also at Philips in Eindhoven in 1958. He tried, his results were, shall we say, not conclusive. He could not rule out the force being zero. The best he could say was that his measurements did not contradict Casimir's prediction. That is a physicist's way of saying, I tried, but the signal was too small and my equipment was too crude. For nearly 40 years after that, the Casimir effect remained largely a theoretical result. People believed it, the math was clean, but nobody could pin it down experimentally with real confidence. Then, in 1997, Steve Lamoureux at the University of Washington built an experiment that changed everything. Instead of trying to align two perfectly parallel plates, which requires absurd precision, better than 100,000th of a radian over a centimeter, he used a gold-coated sphere and a flat plate. The sphere plate geometry sidesteps the alignment problem entirely. He mounted this apparatus on an exquisitely sensitive torsion pendulum, a horizontal bar suspended by a thin tungsten wire, and placed it inside a vacuum chamber. When the sphere was brought within a few micrometers of the plate, the pendulum twisted. Something was pulling the two surfaces together. No charge, no current, no classical explanation. And the magnitude of that pull agreed with Casimir's prediction to within 5%. Let that sit for a moment. A prediction made in 1948, based entirely on the quantum fluctuations of empty space, confirmed nearly 50 years later by direct measurement. The vacuum pushed two objects together. Nothing has muscles. So the zero-point energy is not just a bookkeeping trick. Well, it is not just a mathematical convenience we can subtract away and forget about. It has physical, measurable, laboratory-confirmed consequences. The vacuum is not empty. It has structure. It exerts forces. It is a thing. And once you accept that, you cannot stop halfway. You cannot say the vacuum energy is real enough to push two metal plates together, but let us not worry about whether it does anything else, because it should do something else, something enormous, something cosmic, which brings us to the crisis, the real crisis, the one that keeps theoretical physicists awake at 3 a.m, staring at the ceiling and wondering whether everything they know is wrong. In Einstein's general theory of relativity, all energy is a source of gravity. All energy curves space-time. A photon curves space-time. A hot cup of coffee curves space-time slightly more than a cold one. A compressed spring weighs more than a relaxed spring by a tiny, unmeasurable but done-go amount. Energy is energy, and gravity does not care where it comes from. It does not ask for credentials. It does not check whether the energy belongs to a rock or a ray of light or an empty vacuum. Energy is energy, and gravity responds. So if the vacuum has energy, if the zero-point fluctuations of all those quantum fields contribute a done-go energy density to every point in space, then that energy should gravitate. It should curve the fabric of the universe. It should affect how fast the cosmos expands or contracts. It should show up in the large-scale structure of everything we can see. So how much energy does the vacuum have? This is where the nightmare begins. When you try to calculate the total vacuum energy density, you have to add up the zero-point contributions from every quantum field at every possible frequency. And not just the electromagnetic field, every field. But electrons have a field. Quarks have fields. Neutrinos have fields. The Higgs has a field. Each one contributes its own set of zero-point oscillators, each with its own 1/2 h-bar omega. Now, we do not know physics at all scales. At some point, at extremely high energies, our theories must break down. There is a natural scale where this happens, called the Planck scale, where quantum mechanics and gravity become equally important, and neither can be ignored. The Planck energy is roughly 10 to the 19th times the mass of a proton. It is an energy so enormous that no particle accelerator we could conceivably build would reach it. It is the energy scale where space-time itself becomes fuzzy and uncertain, and the very idea of smooth space starts to dissolve. If we use the Planck energy as our cutoff, if we say we will add up zero-point contributions only from frequencies below this threshold, because above it we genuinely have no idea what we are doing, we get a number for the vacuum energy density. And the number is monstrous. The predicted vacuum energy density comes out to something like 10 to the 113 joules per cubic meter. Let me paint that for you. A 1 followed by 113 zeros. Not total energy in the whole universe, per cubic meter of empty space, of nothing. If this were the real energy density of the vacuum, the gravitational effect would be catastrophic. Space-time would be curved so violently that no atom could exist. No star could form. No galaxy could hold itself together. The universe would either fly apart in an instant or collapse into a singularity. You would not have had time to form a thought, let alone build a telescope or ask a question. Now let us compare that with what we actually observe. This requires a brief detour through the history of cosmology, but it is worth it because the story is wonderful. When Einstein first wrote down his equations of general relativity in 1915, he found something disturbing. His equations described a universe that was dynamic. It had to be either expanding or contracting. It could not just sit there, static and unchanging. But in 1917, everyone believed the universe was static. It had always been there, it would always be there, and it was not going anywhere. So Einstein, uncomfortable with his own prediction, added an extra term to his equations, a constant, a fudge factor, really. He called it the cosmological constant, and its purpose was to provide a kind of repulsive gravity that would balance the attractive gravity of matter and keep the universe from collapsing. Then, in 1929, Edwin Hubble measured the speeds and distances of dozens of galaxies and found that they were all flying away from us. The farther the galaxy, the faster it was receding. The universe was expanding. Einstein's original unfudged equations had been right all along. The universe was dynamic, it was growing, and the cosmological constant was unnecessary. Einstein reportedly called the cosmological constant his biggest blunder. He pulled it from his equations and tried to forget about it. But the cosmological constant refused to stay dead. In the 1990s, two teams of astronomers set out to measure how fast the expansion of the universe was slowing down. They expected it to be decelerating because gravity pulls things together, and over time the mutual attraction of all the matter in the cosmos should be putting the brakes on the expansion. They used distant Type 1a supernovae as cosmic distance markers. These are exploding stars that all reach roughly the same peak brightness, which means you can figure out how far away they are by measuring how dim they appear. What they found in 1998 shocked everyone. The expansion was not slowing down, it was speeding up. Something was pushing the universe apart, something that behaved exactly like Einstein's cosmological constant. A uniform energy density pervading all of space, acting as a kind of anti-gravity, gently but relentlessly driving everything away from everything else. Cosmologists call it dark energy. It makes up roughly 70% of the total energy content of the cosmos. And it looks for all the world like the energy of the vacuum. We can measure how strong this dark energy is by studying the recession of distant galaxies, the patterns in the cosmic microwave background radiation, and the distribution of galaxy clusters across billions of light years. All the measurements converge on the same answer. The observed vacuum energy density is approximately 10 to the minus 9 joules per cubic meter, 10 to the minus 9, compared to the theoretical prediction of 10 to the 113. The prediction overshoots reality by a factor of 10 to the 122, a 1 followed by 122 zeros. I want you to appreciate the scale of this error because numbers this large stop meaning anything unless you find a way to feel them. Consider this. If I told you that a certain room was 10 meters across and you measured it and found it was actually 20 meters across, that would be an error of a factor of 2. Embarrassing, but understandable. If the room were actually 1,000 meters across, that would be an error of a factor of 100. Very bad. If it were the distance to the moon, that would be an error of a factor of about 40 million. Terrible. But this is an error of a factor of 10 to the 122. If you took every atom in the observable universe, roughly 10 to the 80 atoms, and multiplied that number by a trillion, you would still not reach this factor. We are off by an amount that exceeds the number of particles in the entire cosmos raised to a power. Some people have called it the worst theoretical prediction in the history of physics. I am not sure anyone has earned the right to disagree. And yet, and this is the part that really twists your stomach, the theory is not broken. Not in any way we can find. Every other prediction it makes is spectacularly correct. The electron's magnetic moment, the Lamb shift, the running of coupling constants with energy, the existence of the W and Z bosons, the Higgs particle, the spectrum of hydrogen, down to the finest detail. Every prediction lands, every cross-section matches, every scattering amplitude agrees with data. It is as if you had a clock that told perfect time for 1,000 years, never off by a fraction of a second. And then one morning you asked it how much it weighed, and it said 47 trillion tons. You would not throw the clock away. You would stare at it. You would take it apart. You would wonder what you had been missing. That is the cosmological constant problem. Some physicists call it the vacuum catastrophe. And that name is not hyperbole. It is earned. Wolfgang Pauli was one of the first to sense the trouble back in the 1920s when quantum mechanics was still young. Pauli was brilliant, demanding, and famously intolerant of sloppy thinking. He did a back-of-the-envelope calculation, summing up the zero-point energies of the electromagnetic field using the then-known physics, and worked out what the gravitational effect of that energy would be. His conclusion was startling. If the vacuum energy gravitated the way normal energy does, the radius of the observable universe would have to be smaller than the distance from the Earth to the Moon. The entire cosmos, everything we can see with our telescopes, would be crammed into a volume you could practically reach out and touch. He was reportedly amused by the result. He mentioned it to colleagues, but nobody took it seriously. It was treated as a peculiarity, a glitch of the formalism, not a real physical problem. The feeling was that the theory was still being worked out, and these awkward infinities would eventually be tamed. They were not tamed. Decades later, the problem is orders of magnitude worse than Pauli imagined, because we now know about many more quantum fields than just the electromagnetic one, and the energy estimates have only grown. Now, let me tell you about my own role in this mess. Because I am not an innocent bystander, I am one of the people who built the theory that produces these insane numbers. In the late 1940s, Schwinger and Tominaga and I, all working along different paths, developed the modern version of quantum electrodynamics. The basic problem we were solving was this. The earlier versions of the theory, the ones Dirac and others had worked out in the 1930s, gave infinite answers for perfectly reasonable physical quantities. You would ask, what is the energy of an electron sitting in its own electromagnetic field? And the theory would say infinity. You would ask, what correction does the vacuum make to the electron's magnetic moment? And the theory would say infinity again. These infinities were not the vacuum energy infinity I have been telling you about. They were related cousins from the same family, but they showed up in a different way in the corrections you get when you account for all the virtual particles swirling around inside the vacuum. An electron does not just sit there with a bare charge. It is surrounded by a cloud of virtual photons that it is constantly emitting and reabsorbing, and those virtual photons can briefly split into virtual electron-positron pairs, which then annihilate back into photons which get reabsorbed, and those pairs can themselves emit virtual photons and so on, layer after layer, deeper and deeper, an infinite regress of quantum activity happening on timescales so short that no clock could ever measure them. When you try to calculate the effect of all this activity on the mass and charge of the electron, you get infinity. Our solution, the thing we shared the Nobel Prize for in 1965, was renormalization. The idea is this: the bare mass and bare charge of the electron, the values it would have if the quantum vacuum were somehow turned off, are not what we measure. What we measure in the lab is the dressed electron, the physical electron wearing its cloud of virtual particles like a coat. And while the bare quantities are infinite and the corrections from the vacuum are also infinite, the difference between them, the physical observable measurable quantities, is finite. And those finite numbers are what we can predict, and they match experiments to 12 decimal places. It works magnificently. But I will tell you something honestly, I was never comfortable with it. I described it once as a dippy process. Having to resort to such hocus pocus prevented us from proving that the theory is mathematically self-consistent. What we did was design a method for sweeping the infinities under the rug. The infinities are still there. We have not eliminated them. We have not explained them. We have not understood where they come from or what they mean. We found a clever bookkeeping procedure that roots around them. We subtract infinity from infinity and declare the remainder to be the answer. And the astonishing thing is, the remainder is always right. But it nags at you. As a physicist, it nags at you terribly. Because sensible mathematics, as Dirac liked to say, involves neglecting a quantity when it turns out to be small. Not neglecting it because it is infinitely great and you do not want to deal with it. Dirac himself told me at a conference where we were both present that the whole approach was ugly. That before tackling the harder problems of particle physics, we ought to find a truly consistent theory of quantum electrodynamics, one that does not require these infinite subtractions. I agreed with him, I still do. And the vacuum energy is the place where we cannot get away with the trick anymore. When you calculate how an electron scatters off a photon, renormalization works. The infinities cancel in pairs. Beautiful. But when you ask about the total energy of the vacuum itself, the thing that should be felt by gravity, the thing that should curve the cosmos, there is nothing to cancel it against. It just sits there. Enormous, unexplained, and wrong by 120 orders of magnitude. Renormalization solved the problem I could solve, but it left the deeper problem untouched. The vacuum energy was the body under the rug that I was not strong enough to move. So what are the possible solutions? What might explain why the observed vacuum energy is so unbelievably small compared to what we calculate? Let me walk you through the main ideas because they are all fascinating, and they are all in their own way unsatisfying. The first hope was symmetry, specifically a symmetry called supersymmetry. In the 1970s and 80s, physicists noticed something interesting about the zero-point energies of different types of fields. Bosonic fields, the fields associated with force-carrying particles like photons, contribute a positive zero-point energy. Fermionic fields, the fields associated with matter particles like electrons and quarks, contribute a negative zero-point energy, positive and negative. If every boson had a fermionic partner with exactly the same mass, the contributions would cancel exactly. The total vacuum energy would be zero. Problem solved. And this is the elegant promise of supersymmetry. It doubles the particle zoo, giving every known particle a superpartner. The photon gets a photino. The electron gets a selectron. The quark gets a squark. Yes, those are the real names. Physicists are not always creative with nomenclature. and if the symmetry were exact, the vacuum energy would vanish perfectly. Except supersymmetry, if it exists at all, is not exact. It is broken. The superpartners must be much heavier than the particles we know, which is why we have not seen them at any accelerator, including the Large Hadron Collider, which has looked very hard. And when supersymmetry is broken, the cancellation is not perfect. You get a leftover vacuum energy that is smaller than the raw calculation, yes, but still enormously larger than what we observe. Supersymmetry reduces the problem from 120 orders of magnitude to maybe 60 or so. That is a big improvement, but it is like saying your house used to be engulfed in flames and now it is merely an inferno. Better, certainly, but you still cannot live in it. The second idea is more radical. Weinberg proposed it in 1987. Imagine the cosmological constant can take different values in different parts of a vast multiverse. In some regions it is huge and positive, and space expands so violently that nothing ever forms. No atoms, no stars, no observers. In some regions it is huge and negative, and space collapses into itself almost immediately. Only in the rare regions where the cosmological constant is very, very small, just barely large enough to allow the expansion of the universe to proceed gently enough that galaxies form, stars ignite, planets cool, and eventually some curious creature evolves that is clever enough to build a telescope and measure the cosmological constant, only there will anyone be around to notice. We see a small cosmological constant because we exist. If it were much larger, we would not be here to complain. This is the anthropic argument. It is logically consistent. When the accelerating expansion of the universe was confirmed in 1998, more than a decade after Weinberg's proposal, some people pointed to his earlier reasoning as evidence that the anthropic approach might actually work. He had, in a sense, predicted that the cosmological constant would be small but not zero, which turned out to be correct. But it bothers many physicists. It bothers me, because it does not explain why the constant is small. It just says that large values are not compatible with observers who ask questions. It replaces a mechanism with a selection effect. It is like asking why you found a coin on the sidewalk and being told you found it because you were looking down. If you had not been looking down, you would not have found it. True, but deeply unsatisfying as an explanation of why the coin was there in the first place. The third possibility is the most humble and perhaps the most honest. We are using the wrong theory. Our current quantum field theories are what physicists call effective theories. They work beautifully at the energies we can probe, but they are approximations that break down at much higher energies. The correct theory, the one that truly unifies quantum mechanics and gravity, whatever it turns out to be, would presumably give a sensible, finite, correct answer for the vacuum energy. This is probably the most widely held hope among theoretical physicists. And it may well be justified, but we do not have that theory. We have candidates. String theory is the most prominent, but string theory, rather than predicting one unique value for the cosmological constant, appears to predict an astronomically large number of possible vacuum states, something like 10 to the 500 different configurations. This has been called the string landscape, and it has not so much resolved the mystery as replaced one impossible number with an incomprehensible landscape of possibilities, which brings you right back to the anthropic argument through the back door. We are not stuck for lack of effort or imagination. We are stuck because the problem runs deeper than any tool we currently possess. So where does all of this leave us? It leaves us with the most basic, the most primitive, the most fundamental question in all of physics being completely unanswered. What is empty space? We know it is not empty. The Casimir effect proved that. We know it has energy. Quantum mechanics demands that. We know that energy should gravitate. General relativity insists on it. And yet when we compute how much it should gravitate, we get an answer that would blow the universe apart or crush it into oblivion in the blink of an eye. And the universe rather stubbornly persists. Something is canceling almost all of that vacuum energy. Something is reducing a number of unimaginable vastness down to a whisper, and we have absolutely no idea what that something is. Let me tell you why this matters beyond the equations, beyond the chalkboard. When people talk about understanding the universe, they usually imagine exotic, dramatic things. Black holes swallowing stars. The first microsecond after the Big Bang, neutron stars spinning 1,000 times per second. They think understanding means exploring some distant frontier. But this problem is not about some exotic corner of the cosmos. This problem is about the ground you are standing on, the air around you, the space between your fingers, the emptiness inside every atom, which is by volume almost entirely void, the thing that is everywhere, that underlies everything, that is the stage on which all of physics plays out, the vacuum. And we do not understand it. Every time I sat down to calculate a Feynman diagram, every time I drew those little lines and vertices and summed up the paths that a particle could take from here to there, the vacuum was there in the background. It was in every propagator, every loop, every virtual process. The vacuum was not just a blank canvas, it was the most complicated thing in the picture, teeming with particles flashing in and out of existence, borrowing energy from the uncertainty principle for the tiniest fractions of a second, popping up in pairs and annihilating before any detector could catch them. Virtual particles, people call them. And that name is a bit misleading because it makes them sound imaginary. They are not imaginary, but they are not like regular particles either. A regular particle, a real particle, is one you can detect. It hits your detector, it leaves a track in a cloud chamber. It knocks an electron out of an atom, it has definite mass and definite energy, and it obeys the usual relationship between energy and momentum. A virtual particle does not obey those rules. It borrows energy for a brief moment, existing on credit from the uncertainty principle. The more energy it borrows, the shorter the time it can exist. A very energetic virtual particle lives for an absurdly short time, far too short for any instrument to catch it directly. But that does not mean it has no effect. On the contrary, these virtual processes are responsible for some of the most precisely measured effects in all of physics. The Lamb shift is the clearest example. Willis Lamb measured it in 1947, using precision microwave spectroscopy on hydrogen atoms. He found a tiny splitting of two energy levels, the 2s1/2 and 2p1/2 states, that should have been degenerate, identical in energy according to Dirac's beautiful relativistic equation, but were not. The levels differed by about 1,000 megahertz. A small amount, about 4 millionths of an electron volt, but unmistakable, repeatable, real. Where did that splitting come from? From the vacuum, from virtual photons and virtual electron-positron pairs modifying the electric field of the proton as experienced by the orbiting electron. The vacuum between the proton and the electron was not passive, it was active. It was screening the charge, polarizing like a dielectric substance placed in an electric field. Empty space was behaving as if it were a material. And that measurement, Lamb's measurement, was the crack that opened the dam. It was the observation that launched the entire program of modern quantum electrodynamics. The vacuum forced our hand. We had to take it seriously. We had to calculate what it was doing. And when we did, we got answers that matched experiment perfectly, for everything except the vacuum's own total energy. So the vacuum is not just connected to the cosmological constant problem in some abstract theoretical way. The vacuum is connected to everything, to the mass of every particle, to the strength of every force, to the stability of every atom. If you changed the vacuum even slightly, you would change chemistry, biology, the nuclear reactions inside stars. Every galaxy, every planet, every living thing is a pattern of disturbance riding on top of the vacuum state. We are waves on an ocean we do not understand, and there are hints that the ocean is deeper than we thought. Consider what we believe about phase transitions. Water freezes into ice, and its properties change dramatically. Same molecules, completely different behavior. In particle physics, we think the vacuum itself has undergone phase transitions. The Higgs field, which gives particles their mass, sits in a particular vacuum state. In the very early universe, before things cooled down, before about a trillionth of a second after the Big Bang, that field may have been in a different state entirely. The symmetries were different, the particle masses were different, the forces behaved differently. If the vacuum can change states, if it is not the one and only possible ground state, but merely the particular ground state we happen to inhabit, then the question of why we live in this particular vacuum with this particular absurdly tiny cosmological constant becomes even more pressing and more troubling. Are we in a stable vacuum or a metastable one? Could the vacuum we live in be a temporary valley, not the true lowest point from which the universe could in principle tunnel to a deeper, more stable state? And if it did, what would happen? The masses of particles would change. The strengths of forces would shift. The very structure of matter would transform. A bubble of new vacuum would nucleate and expand outward at the speed of light, replacing our physics with something else entirely. The chances of this are, by all calculations, fantastically small. But the fact that we can frame the question at all tells you something about how strange and rich the vacuum really is. Nothing is not nothing. It is a state, one particular state among possibly many. And the properties of that state dictate the properties of everything that exists within it. Let me try to say what I honestly think the situation is. I think the vacuum energy problem is a signpost. It is nature waving a flag, saying, pay attention, you are missing something. It is telling us that the marriage between quantum mechanics and gravity is not just incomplete but fundamentally inadequate at the deepest level. We have tried to combine these two frameworks using the tools we have, effective field theory and semizolical approximations and perturbation theory, and we get 120 orders of magnitude of nonsense. That level of failure is not a small mistake you fix with better arithmetic. That is a flashing beacon saying you need new ideas. Different ideas we have not had yet. Quantum mechanics tells us the vacuum has energy. Gravity tells us that energy should curve space. When we put those two statements together naively, we get a disaster. The resolution must lie in a deeper understanding of how quantum mechanics and gravity interact, an understanding we do not yet possess, an understanding that will require, I suspect, a revolution comparable to what happened in the early 20th century when quantum mechanics and relativity came on the scene. And until we have that understanding, the simplest thing in the universe, a patch of empty space, will remain the most mysterious. I told a younger colleague once, around the time of the Nobel ceremony, that I thought renormalization was a first step, not a solution. That the real breakthrough would come when someone understood the vacuum, understood it the way we understand atoms, or electromagnetic waves, or the motion of planets, not just mathematically, but physically. What is it made of? What determines its energy? Why does it have the properties it has? I still think that the vacuum is where the next revolution will come from. Whoever cracks it will change everything, because every particle, every force, every structure, every law of physics sits on top of the vacuum state. Get the vacuum wrong, and you get everything wrong. Get it right, and you might just get everything right. And right now we have it wrong by 120 orders of magnitude. Some people find that discouraging. I find it thrilling, not comfortable, not reassuring. Thrilling in the way standing at the edge of a cliff is thrilling, because it means there is something enormous we are missing. Not some decimal point adjustment, not some minor correction to a coupling constant. Something profound, something that will reshape how we think about space and energy and the relationship between what is very small and what is very large. It is out there, hiding in the silence between the plates, in the jiggle that cannot be stilled, in the mismatch between our finest equations and the actual behavior of the cosmos. People sometimes ask me whether physics will ever be finished, whether someday we will have all the answers and there will be nothing left to discover. And I always laugh when I hear that question. Finished. We do not even understand empty space. We do not understand the thing that everything else is made out of. We are like children who have learned to swim beautifully in the ocean, but have never thought to ask what water is. The vacuum is the water, and until we understand it, everything else we know, everything, floats on a mystery. Nothing is the biggest unsolved problem in physics. And the strange truth is we have been staring at it our entire lives. We are surrounded by it. We are soaking in it. Every experiment ever performed, every observation ever made, every breath you have ever drawn took place inside the vacuum, and we do not know what it is. There is a riddle buried in the heart of empty space. It was there before we were born. It will be there after we are gone. And so far the universe is keeping its mouth shut. What do you think is hiding in empty space? If you had to place a bet, what is the vacuum really made of?